ratio for a finite output current resistance R naught, which was 170 kilo ohms. This was the finite output resistance of the transistor M4 due to the finite channel width modulation parameter lambda that is not zero. So that is 170k, and owing to that, we have this factor over here for the cone mode gain, which turns out to be finite. If R naught is infinitely large, then ACM is zero. So if you're going to substitute this for an expression ACM together with the values of RD, that is 16 kilo ohms, the drain resistors, and the conduction parameters and the quiescent currents, well, you will have a finite but small cone mode gain, and owing to that, you will have a probably small cone mode rejection ratio if the cone mode is not exactly zero. So the value of the cone mode rejection ratio can be increased by increasing the output resistance of the current source. Well, what we are trying to do is we are going to make the cone mode gain equal to zero for a very high output resistance. So an increase in the output resistance can be accomplished by a more sophisticated current source circuit. So instead of having this configuration of the current mirror circuit, what we can do is to employ a cascade current source, MOSFETs. So there are four MOSFETs connected in this fashion, in cascade fashion. So now in chapter 10, the output resistance of this configuration is given as R0 is R0 4, R0 2, then 1 plus GM R0 4. So for these parameters, if you take the parameters from example 11.9, so for this parameter, if you take n equal to 1, and R naught can be taken as 170 kilos, and for same values of RD, for example, RD is not required, but anyways, the transcriptance gain is there. TM is under twice Kn IQ. IQ is 0.587, under root 0.587 divided by 2 is again 1.53, and if you substitute for R0 R4, R0 4 is 170 kilo ohms, then you have this output resistance is considerably higher than 170 kilos, that is 444.6 mega ohms in this case. And if you plug this value instead of 170 kilo in cone mode gain, you will find out the cone mode gain has been reduced considerably. Okay, and this effect is going to increase your cone mode rejection ratio. So again, using the parameters of 11.9, the cone mode voltage gain of differential amplifier with cascade current mirror would be, so in this configuration your cone mode gain is reduced significantly, and this turns out to be, and this makes the cone mode rejection ratio considerably higher. So you see from 45.3 dB, this is 93.7 dB. So we increase the cone mode rejection ratio dramatically by using the cascade current mirror instead of a single two transistor current source. So what we've done is from these two transistor current source M3 and M4, we have replaced this by a cascade current source, and which has a very high output resistance. So you note that, however, the differential mode voltage gain is unchanged. So in both configurations, because this is just providing you with the reference current for biasing of the MOSFETs M1 and M2 in both the configurations, but all you need was to have a higher output resistance for the current source. So to gain an appreciation of the difference in CMRR between 45.3 dB and 93.7 dB, we can consider the linear scale. So if you take the antilog of that, you'll find out that 45.3 dB means the differential gain is a factor of 185 times larger than the common mode gain, while CMR dB of 93.7 is 48,000 times larger than the common mode gain. So there's a huge difference between 93.7 and 45.3. So once it rose to 93.7 on the linear scale, it means 48,000 times the differential gain. So that's what it is. The differential gain is a factor of 48,000 times larger than the common mode gain. So it is so much large. So all we need in the design of a differential amplifier is to have a differential gain as much as possible, as large as possible, and the cone mode gain should be as small as possible. Okay, so CMRR, which is AD over ACM, ideally should be infinite. Okay, it should be large. It should approach infinity, and that is only possible if R naught is large. If R naught approaches infinity. Okay. All right. Now, so far we have talked of single-sided output. So, for example, in this configuration for the small signal analysis, we consider the the output from the drain of M2. Now, what if we have a two-sided output? Okay, so we can have V01 and we can have V02, okay, which is VD2, and this V01 is VD1. So, what if we have a differential amplifier with two-sided output? So, if we consider the two-sided output of an ideal MOSFET op-amp, it's not op-amp, it's MOSFET amplifier. So we define the output V0 as VD2 minus VD1. Okay, so now I have VD2 minus VD1. This is actually VD1. Okay, so this is the difference of these two drain voltages. So my two-sided output is I'm taking the difference of the drain voltages of two MOSFETs M1 and M2. And if you just recall that what we discussed in the last video was that we had an output voltage in terms of your differential gain AD and the common mode gain ACM, right? So AD was basically GM by 2 RD, okay, GM by 2 RD, and but now you will see if you carry out the same analysis, you will find out that for two-sided output, when V0 is VD2 minus VD1, we can show that the differential mode voltage gain, if you carry out the same analysis that we did last time, starting with the KCL at Vs node, and then formulating an expression for Vs, and then putting this into the output voltage. Now this output voltage, so now we will have, for example, we will have VD1 as well. Okay, this is V0. This is V02, this is VD2. So VD1 is also equal to now minus GM RD. Okay, since GM is the same, and then you're going to have what? V1, so which is V1 minus VS1. VS source is the same. Okay, and if you want to take the difference of these two equations, so you will have because of V2 and Vs, you will have a difference of V2 minus V1, okay, and Vs is going to go out, for example, over here, and the expression that you're going to have is GMRD, right? This will be, for example, this will be the output voltage. If you take the difference between this expression and this expression, well, this will, if you want to do that, so let's do it, minus GM RD, then V1 minus Vs, then it will be minus V2 plus Vs. So the Vs is going to cancel out, and we are going to left with the differential voltage Vd. This is minus GM RD into V1 minus V2, which is the differential voltage. Okay, and this happens to be the differential gain of a two-sided MOSFET amplifier, differential amplifier. So this is what it is. We have the same expression. So AD is GMRD, which is basically your V0 by VD, right? Or in this expression, if you take VD on the other side, so I'm going back again over here. So again, this was the difference. So you just need to take this VD on this side because the difference of the output voltages. So this is not AD actually. This is V02 VD2 minus VD1, and then divided by basically. So this is your output, two-sided output, divided by the differential voltage. This is equal to minus GM RD. Okay, minus GM RD. So again, you will see that ACM ideally will be 0, and for a two-sided output, AD is simply GMRD. AD is simply GMRD. Differential gain is GMRD for two-sided output, and the common mode gain is 0. Okay, so I mean there's nothing left. There's nothing left more over here. So this is 0. Nothing over here. Okay. Because the output is just consists of a single expression. There are no two expressions, so there are no two. So you won't have this expression. So ACM is simply 0. Okay. The common mode voltage gain given by is ACM is 0. So the result of ACM 0 for two-sided output is again the consequence of using matched devices and elements in the differential circuit. So it says that if you have the same MOSFETs, the MOSFETs are matched. That is, for these two MOSFETs, the GM are same. Okay, the transconductance gains are same, RD is same. Okay, so you will have these same expressions. But what if there is a difference in RD, and what if there is a difference in the transconductance gain of two transistors? Then there will be a finite common mode gain. Okay, and it's not the difference VD1, the drain of first MOSFET, and the difference of the drain voltage of second MOSFET is not simply minus GM RD into VD. It's not simply the difference of these two voltages, V2 minus V1, V1 minus V2. Then there will be some more terms due to the difference in RD of two drain resistors, and due to the difference of GM. So therefore you will have this expression again in terms of again you will have this expression V0 in terms of AD VD minus AM ACM VCM. So you will have a finite common mode gain if there is a small shift in the transconductance gains of the two transistors. So let us reconsider the two-sided output again to discuss the effects of mismatch elements. So mismatch is, first we are going to discuss this, what happens if there's a mismatch in GM, the transconductance gain, and second is what happens if there's a mismatch in the drain resistors. Okay, so now we assume that RD1 and RD2 are the resistors in the drains of M1 and M2. So RD and RD2 over here, now it's RD1 and RD2. Okay, and let's have this as VD1. Okay, this is a two-sided output. So if the two resistors are not matched, we assume that we can write RD1 as RD plus delta RD, and RD2 is RD minus delta RD. Then using a small signal equivalent circuit, we can still find the differential gain is the same, but then ACM comes into the picture, that is delta RD over R0. So if delta RD is small, if it is 0, ACM is 0, common mode gain is still 0, and you will have a very large common mode rejection ratio. But if the elements are mismatched, then there is a finite common mode gain. Similarly, so you will have a finite, still a huge common mode rejection ratio, but this is only due to the finite difference in the drain resistances. Then let's have a look at the effect of similar effect of transconductance mismatch in a two-sided output. So we can consider the effect of transistor mismatch by considering the effect of mismatch in the transconductance gain GM. So we assume GM1 and GM2 are the transconductance parameters of two transistors in differential amplifier, and assume that GM1 is GM plus delta GM, GM2 is GM minus delta GM. Again, using a small signal equivalent circuit, we find that the differential mode voltage gain is AD is GMRD, and the common mode gain is the differential gain stays the same, but common mode gain is due to the difference in GM. You will have a finite common mode gain, and then CMRR is have a very similar expression to what we had for the difference in the drain resistance. So there is a similar expression for the difference in the transconductance gains. So, but in ideal case, if the transistors are matched and you're taking two-sided output, then the differential gain stays the same, that is GMRD, the common mode gain is 0, and this implies that common mode rejection ratio is infinitely high. Okay, so common mode rejection ratio is infinity. This is infinity. Okay, all right, that's it.